If you have performed an investigation in which you took the temperature of ice as it heated up, went to liquid, and then eventually boiled, you may want to know more about what's actually happening. So we're going to show you how to interpret heating curves like that. And from the graph showing the temperature of a substance and the time the temperature was recorded, we can determine what was probably happening down on the molecular level that you can't see. This is the kind of heating curve that you get when you heat a measured mass of ice, or any mass of ice. A temperature probe is used to follow the temperature with respect to time. And you can see the temperature is going up in this area AB. It's staying constant in the area BC. Then between C and D, it's going up. Then it remains constant for a longer period of time between D and E. And then at this point, we see an increase in temperature as a function of time. The macroscopic observations should also be added, and you should have made those in your investigation. You probably noticed that between A and B, the probe is kind of stuck in the ice or in the ice slush. At CD, the temperature is going up and you have a liquid water. There is no ice remaining at all. And then between D and E, as that temperature stays the same, you have what we call a rolling boil. Bubbles of steam are forming throughout the water, and it really doesn't matter where it is, there's going to be some bubbles close by. You did not observe the area EF because if the experiment was conducted properly, you stopped before all the water boiled away. Now let's interpret. First, we have to remind ourselves of what energy is. And energy is expressed in many ways. There's heat, electricity, there's mechanical energy that, for instance, turns the turbines in a dam-generated water turbine. And of course, there's light energy as well. Energy is classified into two categories. Kinetic energy is energy of motion. That's the energy that you're showing when, say, you're running a race. And potential energy is energy of position. This is going to require a little more explanation. You can convert kinetic to potential and potential to kinetic energy. If you take an object that's, say, 5 feet off the floor and drop it, the energy is originally potential, stored energy of position, and it gathers speed, and eventually it hits the floor and gives off a noise. Those are all expressions of kinetic energy. But if you recharge a battery, say by using a hand-operated electrical generator, you're taking kinetic energy, that is energy of motion, and turning it into chemical potential energy in the battery. Let's talk about what's happening at each phase of your heating curve. As the ice is heated, not as it's melted, but as it's heated up towards where it's going to melt, the molecules of water are fixed in a crystal lattice. They're solids. They vibrate faster and the temperature goes up. So as they get faster and faster, the temperature goes up, but they're still held in this crystal lattice. At the melting point, the crystal lattice is breaking up, but the molecules are not vibrating any faster. They're just getting out of position so they can slide over each other, as you see in a liquid. Because liquids are fluids, they can pour. Between 0 and 100 degrees Celsius, the molecules of water in the liquid state vibrate faster and faster and faster, but they stay about the same distance apart. The kinetic energy is increasing, but the potential energy, the energy of position, is not increasing. Now, towards the end of that, you start seeing evidence of vapor coming off the heating water. We call this the vapor that's creating the vapor pressure of water. But at about 100 degrees, and that depends on the atmospheric pressure, all of the molecules of water have enough energy to escape the attraction of the other molecules, and you see this rolling boil because steam is forming in every part of the liquid. That's what we call a rolling boil. And so what in this case, the energy of position is changing even though the kinetic energy is not. And instead of just vibrating inside the liquid, they're now throwing off and heading off into the atmosphere. So this is a change in position from being stuck in the liquid to being free in the gaseous state. The kinetic energy actually doesn't change as it goes from liquid to gas. What's changing is the potential energy. So while the water is boiling, the temperature does not increase because the kinetic energy doesn't increase. This is our interpretation of your warming curve. Here we go. Here, AB, kinetic energy is increasing. The ice is warming up. Here, the kinetic energy is constant. Potential energy is increasing, but kinetic energy and temperature are not increasing. Here, the kinetic energy is increasing, which is measured by the increasing temperature. Here, as the water boils, the kinetic energy is constant, but the potential energy is increasing. And past that, you're just heating up the steam and making the gas molecules go faster.